Today we're going to tackle a problem where we have three identical tanks that drain sequentially in series. And at its steady state, we define that we have some liquid level in each of these tanks. So we'll call this H1, H2, and H3 for each of the three tanks. We're going to have some liquid level in each of these three tanks, as well as we're going to have a steady flow rate. And of course, this will trickle down. So eventually we get to this flow out of this last tank. So the first thing we want to do here is we want to model the draining of the water from each tank as a model of time when we take this steady state system and increase Qn. So we're going to increase Qn by 10%. So let's decide some parameters. So we'll define Qn as 0.5 meters cubed per second. And I want to also define the cross-sectional area. The cross-sectional area of each of these tanks we'll call A. And that'll be identical for all three of the tanks. That's how the problem is set up. So A, we will say, is 1.2 meters squared. This is the cross-sectional area of each tank. Now, I also want to define area of the outlets at each of these tanks. And we'll define the area of that outlet as 0.2 meters squared. Now the next thing that I'm going to write out here is, well, we want to simulate the heights, the liquid level heights in each of these tanks as a function of time. Now the two things that we know is that we know we have a volumetric flow rate, and we know we have an area, and one more thing that we know is that we have some height as well for each of these tanks, which is the thing we're trying to model. So if I were to model this, I would probably use something that looks like this, where we have a change in volume over time. And the reason why we use volume here is because the volume of liquid in these tanks is equal to the cross-sectional area times the height. So we can rewrite volume as, or we can rewrite dV as ADH, area, which remains constant, times the change in height. And this is all going to be over time. So we can actually write these for each of the tanks. So if I were to say I here, I is equal to 1, 2, 3. It's equal to each of these tanks here, because each tank has some height that will vary with time. The cross-sectional area remains the same, and it's following the same time axes. So this is a good starting point. And the next thing that we can also take a look at in terms of mathematically modeling this is we'll take a look at Bernoulli's equation. And Bernoulli's equation looks something like this. Over 2 equals 0. Now, let's make some assumptions that'll make this a little easier to solve. Now, looking at this tank, we are assuming that these tanks are open to the atmosphere. And so atmospheric pressure, obviously, is going to be the pressure acting on the surface of our liquid level here. So we know what the pressure is at position 1. Call this position 1. Position 2, this is an opening that we're also assuming is open to the atmosphere. So atmospheric pressure is actually acting on our inlet, albeit a rather large inlet, and our outlet, which is a lot smaller. So we can say that our first simplification is going to be that P2 is equal to P1, which is equal to PATM. So that's our first assumption. We know what Z2 and Z1 are. That's going to be 0. We'll start at some position. We'll start at some height. That'll be the liquid level here. And we'll go to 0, which is the bottom of the tank. So 0 to H. We know what that's going to be. And our second major assumption that we're going to make actually has to do with our velocities. What we're going to end up saying for our velocities is, well, we've defined that our cross-sectional area is 1 squared meter more than the area of our outlet. Therefore, we are probably going to have a much higher velocity coming through our outlet than we will our velocity of the fluid at the cross-sectional area. Which makes sense because we have a much smaller opening and we're trying to force the same amount of fluid, more or less, through a smaller opening. So our second major assumption is that velocity at the opening far outweighs the velocity at, the velocity at the outlet far outweighs the velocity in the tank. So here are the two assumptions that we can make. Our first assumption ends up canceling out this entire term here because P2 minus P1 is going to be equal to 0 since we set these equal to each other. And since V2 is far greater than V1, we can ignore that V1 exists here and we just are left with V2 squared over 2. So making those assumptions, we get Z2 is going to be 0. Z1 we defined as H. And this is height of whatever tank that we're talking about is. And then we're going to add V2 squared over 2 equals 0. Now let's put this term on this side. V2 squared over 2 is equal to, this is minus G times HI. So if we put it on this side, it'll just be G times HI. And the last step to get V2 isolated is to multiply this term by 2 and take the square root. And so now we know the velocity exiting the tank as a relation to the height. And we got that using the Bernoulli equation. So now let's combine this part. I'll highlight it. We want to combine this, and we want to combine this. So now we have, we're going to set up a differential equation that we can solve in Python to help us model this data. And I'll do it here. Why not? So we want to combine the fact that we have our change in volume over time. We're modeling this as the cross-sectional area times the height of the tank in question, change of the liquid height in the tank of question over time. And we know that this is the change in volume depends on the volumetric flow rates. Well, quite literally, if we look at dV dt, this is the change in volume over time. So this is going to be equal to some volumetric flow rate, I minus volumetric flow rate of J. These are two tanks in question of tank IJ, or however you define it. So the same thing we can also write down here, where we're saying that for whatever tank we're looking at, we have the volumetric flow rate. Let's just say this for tank 1, just to be able to use these attributes that we've defined. So the difference in the flow rates is going to be equal to Qn minus Q1, which is the flow exiting tank 1. So Qn minus Q1. Now, a volumetric flow rate has the units of meters cubed per second. Well, we can get this if we do a sort of dimensional analysis. We get this by multiplying a velocity, meters per second, times an area, meters squared, gets us meters cubed per second. Well, if we look at the velocity at the outlet, we have defined that using Bernoulli's equation. And if we want to look at an area, well, we've defined what the area of the outlets are. It's 0.2 meters squared. So we have these two knowns for which we can substitute for our volumetric flow rates. So I'm going to rewrite Q1. I'm going to rewrite it as area of the outlet times the square root of 2 times gravity times the height in tank 1. And this is equal to the flow exiting tank 1. Now, one last thing I want to point out here before we go into Python and start writing some code is, well, let's go back to the definition of this problem set. We stated that we have 3 identical tanks that drain in series, meaning that the outlet of one tank is the inlet for the next tank, except for, of course, our flow that we control, the inlet flow. So we have 3 identical tanks, and running this in steady state means that the heights of each of these tanks are not changing. They are steady, meaning that the flows out are also not changing. So if we have 3 identical tanks running in steady state where each tank is draining in series, we can make the conclusion that the heights in each of these tanks at steady state, so at steady state, the heights within each tank has to be identical. Has to be identical, which is to say that H1 is equal to H2 is equal to H3. So right now we'll define this as height at the steady state, at the initial steady state that we have set this problem up with. At t equals 0, we're defining the system at steady state. And at t equals 0, it is at some height. And we can calculate that height by using this relationship here. So I'll write this back out. So Q1, I'll just use it as an example since we've been using it so far, is equal to area of the outlet times the square root of 2gh1. So first step, Q1 over A out. We'll divide over by the outlet area, then we'll square this and divide by 2g. Divide by 2g is equal to height 1 equal to height at the initial steady state. So now we can throw some code in Python to help us model the change in the liquid height level within each tank as a function of time. So far, I've just imported a couple libraries. I've imported NumPy and I've imported a make subplot from the Plotly library, as well as importing solve IVP from the SciPy integrate library. Now, I mentioned before that we have now set up this differential equation for which we can set up the change in height as a function of time. And instead of running that calculation by hand, what we can do is we can tell Python that we have some function that we want to solve for, and if we give it enough inputs, it'll do it for us. So that should connect, and that should give us all these libraries imported. So first things first, let's start defining our parameters, our process parameters. So we know three things so far. We know the Q in at the steady state, at the initial steady state, is equal to 0.5 meters cubed per second. I'll just toss the units in a little comment here. We know the cross-sectional area is equal to 1.2 meters squared. We know the area of the outlets are equal to 0.2 meters squared. And we'll throw gravity in there because we are going to end up using gravity. Gravity is equal to 9.81 meters per second squared. Right? So here are our knowns. And I also want to calculate the initial height at the steady state at time equals 0. So call something h subscript steady state, or underscore steady state. And if you remember what we just derived, it's Q1 over area of the outlet squared over 2G is equal to our steady state height, which is true across all of our tanks at the initial steady state. So putting that in, so we have our Q in at the initial steady state times our area of the outlet, or divided, this is over, squared, and this is all over 2 times G. All right, so now we have everything that we know so far in terms of our process parameters, and then we can start getting into coding the function that we will be using to solve the differential equation using solve IVP. So let's start coding in our function. I'm going to define a new function, and we'll call it RHS. That's going to stand for the right-hand side, and I'll show you why that is in just a moment. And the inputs that we want for it, we want an input of time, and I'm going to define some vector down here. And I'm going to unpack this vector into our 3 heights. So that'll be the first thing I do. Now, I also want to know the flow rates. Q2 and Q3. Well, initially we know that these 3 flow rates are exactly identical, because initially we are at t equals 0, we are at a steady state. And if we're at a steady state, that means the height of the liquid level in each tank is not changing, which means that Q in is equal to Q out. So Q in is equal to Q1. And the same thing goes for tank 2. We have a flow in has to be equal to the flow out. We're working at steady state. And we talked about this already, right? So how do we get the liquid height levels? Well, if we want the heights, or not the heights, if we want the flow rates, we follow this equation right here for I equals 1, I equals 2, and I equals 3. So coding this into Python will look something like this. So for tank 1, we are going to use the outlet area times np.square root. This will take the square root of our function. 2 times g times h1, which we are unpacking from this vector, right? So this this is the flow rate out of tank 1. And we're going to do the same thing for tank 2. And one last time for tank 3. And this will save it into its respective variable that we define here. Now, one thing that we're going to do, because this is in the definition of the problem, is we have our initial steady state. That's fine and dandy. But we want to change it by some parameter. So for right now, just to keep everything in steady state and make sure that our graphs are working good and to show that solve IVP is solving it correctly, we'll keep this Qn at time equals 0 equal to the Qn at steady state, right? And then a return. Well, what do we want to return? The goal of this problem is to model the change in height as a function of time. Well, what over here do we have that defines that? Well, pretty easy. We have dh dt. This is the change in height with respect to time. So to get this alone, all we do is we divide the right-hand side of this function by the cross-sectional area. So our left side is our change in height with time. On our right side is our difference in flow rates divided by the cross-sectional area. So let's code this in. We want to return this for each of the tanks, because each of the tanks is going to change height at a different rate once we increase the volumetric flow rate, and we'll show that in just a minute. But for right now, let's just get this coded in. So we want dh dt, dh1 dt is equal to qn, I'll return this as an array. So our first is going to be qn, and right now that'll be, we'll change this to qn not, because we will be able to change this later, minus q1, which we will calculate in our function, divided by the cross-sectional area. So here's our first entry. Put this in parentheses. And we'll do the same thing for this second tank. Our inlet, or our flow rate in is equal to Q1. Flow rate out is equal to Q2. And same thing, we're going to divide that by the cross-sectional area. And one last time, we'll do the same thing for tank 3. So Q2 minus Q3 divided by cross-sectional area. Now we should have successfully defined our function for the right-hand side to be able to solve it in IVP. So let's start coding in our solve IVP function. First, we want to define the time range over which we want to do this this differential solution, the solution of our differential equation. So let's define some end time. 20 seconds sound good? No, not as an integer ratio. So let's do this. We want our result, so I'm going to just call that res, and it's going to be equal to solve IVP. First thing we need to define is our function, which is our right-hand side function. We'll define our time range. So we're going to start at time equals 0, which is where the system is still at steady state, to the end that we design up here. And now the next thing that we need is we need to give it a set of initial values for it to make its guess. And we have an initial value here. It's our height at the steady state. That's what our heights are equal to at time equals 0. But as you see, we have 3 things we want to return. So we need to have 3 initial heights. This is just one initial height here, but there's a way to get around that, which is we'll take our steady state height, and Python does this neat little thing where you can just multiply it by 3. And this will just give you an array of the same value 3 times. So now we have our function, our time range, and our initial values. Now, a couple other things that we want to do we'll switch the dense output of this to true because we don't want a lot of information. We just want what we need, which is our differential solution. And we'll set our method as well, and we'll set this to the Radal method. Radal method. Okay, it seems to have gone smoothly, so let's see what our result output is. As you can see, it says the solver successfully reached the end of the integration interval, and we see that we have now a set of values for each of the three things that we wanted to return, which is our three change in heights over time. Now, you look at this and you say, well, these are all equal to each other. And that should be the case, because if you look at our steady state height, this is equal to that. And that's because our initial height at time, or our initial flow rate at time equals 0, right now is just equal to our steady state flow rate that we had this entire time, which is used in the steady state calculation. Now, if we wanted to graph this, so let's make a subplot. Fig equals make subplots. Even before this, I'm gonna set up my plot range for a time. So tplot. We'll go np dot linspace to give us a set of times from 0 to our specified end time. Let's say we want 1,000 values. Sure. So we'll go fig.add scatter. Our x value is going to be our time, so the time that we plot, not necessarily the end time. And y is going to be our solution in our result, so res.sol is how we get our solution, over the time range t plot that we set. Set mode equal to markers. Put that in. And yeah, let's see what happens. So right now it's trying to plot all three things at once. As you can see, it's starting to it's not necessarily exactly what we need. It's kind of just smushing all three lines into one set. So I think the best thing to do here is we'll store our solution here into a separate array, and we can just call this our line of interest. So right now you see that for the tank height in tank 1 remains exactly the same. And if we want to see the other ones, I'll name these as well. H1, right? I just gotta copy paste this 2 more times. So I'll do one for H2, one for H3. And now you see that we have all three lines plotted exactly on top of each other because it is at steady state. We start at time 0 and at time equals 20. We have 100 plots and we have 1,000 plots in the middle here, but it doesn't change not one bit because again we are at steady state. So let's spice this up a little bit. Now in the design of our problem, we said that we were gonna take the steady state system and we're going to increase the flow rate of the inlet by 10%. So what that looks like is our Qin now at time equals 0 is no longer the steady state flow rate, but now it's going to be but it's going to be 10% more than the steady state flow rate. Do this, it's all great. And there we go. We see now that tank 1 sees the steepest increase in the height. Maybe just change this to lines. We don't need markers. This isn't really plotting data. It's just plotting a solution. There you go. Looks a lot nicer now. We see that tank 1 increases the greatest. It has the greatest rate of change compared to the other two tanks. And at some time down the line, maybe at 16 seconds or so, we find that the new tank heights are pretty close together and is now approaching a new steady state that is defined by the new flow rate that we give the problem. So now we successfully modeled the change in the liquid level height in each of the tanks as a function of time when we increase the flow into the first tank by some number like 10% as compared to the steady state flow rate. But in real life process controls, we might want to work backwards. We might want to say, well, what if I want to change the set point of tank 3? So we'll make this stand for the set point of the third tank. Let's say I want to set that to 10% of the steady state height, or 10% more compared to the steady state height. So something like SS times 1.1. So now we are no longer defining the flow rates, rather we are defining the height, and we are controlling the height, because if we look in a tank in a real life process automation, we are working with level sensors, we're working with level transmitters, and we might have some desired set point for the liquid height level in those tanks. So that's just what we're trying to simulate here. And the way we're going to do that is, first we're going to modify our function, and we're going to say something like, hey, before we were defining the flow rates and changing the flow rates, but now we are going to define the change in our flow rates according to the change that is necessary to meet our new set point in the tank in question. So it might look something like this, where we have our initial steady state flow rate, and we're going to add a term which will be the controller gain. We'll define that in a moment. That's going to be the controller gain times the set point. The set point in this case is higher, so we're changing the set point from its initial H3 at the steady state that we are initially using as an input at time equals 0. So now we see that we haven't defined this KC term, this proportional gain, this controller gain that we have. So we'll start off real nice and easy, 0.1. Maybe we won't even notice this, we don't know. So we have this, which is our controller gain. And this model that we have, where we have our steady state inlet flow, and we're adding on this controller gain times the difference in our set point and our initial height. This is called a proportional only controller. Controller. AKA a P controller. This is the most basic type of process control that we can implement in this. And it also is maybe not the best for this system, but we'll roll with it for now. So now we've defined a controller gain, we've defined a set point for our third tank, and we have defined how that set point interacts with our controller gain. So let's graph it out. Now, this doesn't look too different from what we originally had. just for reference, here is the set point we're trying to meet. This 0.35, we'll call it that, right? So this is the set point we're trying to meet, and so we are going to be adjusting the flow rates in the tanks to the first tank, and by sequence the rest of the tanks in the series, to try and meet that set point in tank 3. So that is exactly what we were looking at here. We're changing the height in tank 1, that changes the height in tank 2, that gradually changes the tank height in tank 3. So obviously 1 didn't get it done. Let's see if just 1 gets it done. Woof. Alright. Still not there. We're only at like 3.4, 0.34, less than that. But now we see this huge overshoot that we have. And then it settles down to some value, which still isn't what our set point is. So apparently this gain doesn't work either. Maybe try a little bit higher. We'll go 3. Woof. Okay. Let me extend this out a little bit more so we can see it all. Now we see that we're having almost oscillations. We have oscillatory behavior in our tank height. And it slowly starts reducing in amplitude until we settle on not even at our set point yet. We're still having a discrepancy between 0.35, our desired set point, and our where our system decides to settle on based on the differential solution. Maybe 5 will get it done. Right, more oscillations. More. Maybe... Right. So now we're seeing that there is a pattern here. As we increase our controller gain, our offset, our proportional offset is what this is called. We have a proportional offset from what our desired set point is, and the more we increase the controller gain, the less stable this system becomes. And what do I mean by stable? Well, let's crank this up a little bit more. 6. Yeah. All right. Now we're seeing lots of oscillations. Lots and lots of oscillations. Even 1,000 doesn't get this entire graph on the page anymore. So we are oscillating a lot here. And it still seems like we're starting to settle even just a little bit. If we crank it up to 7. Right. So now, if we get up to 7, now even our computer is saying these numbers are too big for even us to display. So maybe let's try a little bit lower. Nope, still too high. 5. And now let's see what the graph looks like. Boom. Now see how we're diverging to insanely extreme numbers here. 8 times 10 to the 24th. Unfathomable magnitudes that we have here. So our system has now officially become unstable. Our system no longer is settling at one value. It's diverging to infinity. So now our system has lost its stability. And even back when we had it just at 6, we can see that our system keeps going up and around, up and around, up and around, up and around, oscillating. And we're not really settling even within 1,000 seconds time. So the two things that we look at when we are controlling the controller gain is we look at the proportional offset, which is how much the offset of where this oscillation settles at, how much that is offset from the desired set point that we set by the control, as well as the stability of our system. Does it converge within a reasonable amount of time at the proportional offset value? Are we diverging to infinity because our gain is too high? These are two things that we want to keep in check when we are designing controllers for process automation.